All right, so hello everyone. I was a student at University of Liverpool at the Risk Institute, and I work for UK AEA. And what I'm going to be talking about today is a strategy for propagating unknown dependence assumptions through black box models. So there are a couple of methods for propagating unknown dependence, but not very many. Here's the three that I know of. You can do second order Monte Carlo, or sometimes we'll call it dispersive Monte Carlo, where you essentially repeat Monte Carlo simulations with changing correlation coefficients. And I'll show you in the next slide why that sometimes doesn't work. There's, of course, interval analysis, which is generally a good idea, but if you have some additional probabilistic information, you can't make use of it. And there's, of course, probability balance analysis, or p-box arithmetic, which is an intrusive method and doesn't quite apply in black box models. I'm just going to show you an example of second order Monte Carlo, and I'm going to show you for a very simple summation of two uniform distributions. I'm going to cycle through a whole bunch of correlation coefficients. And what you can see is that the output distribution is really sensitive to the correlation coefficient. And if you do an exhaustive scan of this, you can take some bounds, and what you essentially get is a p-box, this kind of hourglass-shaped p-box. But then if you use p-box arithmetic, which we can do for this simple summation, the true bounds are much fatter. So essentially, if you're using second order Monte Carlo, it wouldn't be sufficient to get the true breadth of uncertainty that you have from your dependence assumption. So for this method, I'm going to introduce an alternative model for uncertainty called the possibility distribution, which Alex spoke about. And to describe that, I'm first going to show you a p-box, which is essentially two bounds on a CDF, and it represents a collection of distributions, which any distribution which falls in the bounds is a member of the p-box. There's an alternative representation of this, which is, if you discretize it, you can think of it as a collection of intervals which are sort of stacked in a staircase-like shape like this. Another way to think about this is that it's a random set, which is sort of a distribution with set valued realizations. But there's another way you can stack these intervals, which is kind of like a pyramid shape. And here I'm just going to sort of make the discretization smoother and smoother, and you get this continuous curve. And this is what you call a fuzzy number, or you can think of it as a consonant or a nested random set. And these fuzzy numbers are unimodal possibility distributions. So there's kind of two ways of viewing a possibility distribution or fuzzy number. So if you think about an interval and its membership function, the membership function or characteristic function of the set is essentially this function which goes from the real line to binary 0, 1. And what a possibility distribution is essentially a continuous generalization of that. So instead of it being a binary 0, 1, it's this continuous function that can give you any value in 0, 1. So that's the kind of membership view of it. And another way of thinking about it is that it's a nested stack of intervals, right? And what I'm going to show you in this presentation, hopefully, is that these structures are as nearly easy as to propagate as intervals. We're also able to bound probabilities with it. So essentially, if you have these dual measures that you can get from the possibility distribution called the necessity and the possibility. The possibility is essentially, let me show you. So if you take a set like this and you want to compute the possibility, which is the upper bound on the probability, you essentially find the maximum value of this function inside the set U. And if you want to find the lower probability, you essentially find the maximum value outside. So for this example here, you can compute this upper and lower bound on the probability. So for example, for the set U here, you get this interval bound on the probability of 1/4 to 1. Another way of bounding probabilities with it is using the alpha cuts. So we essentially take one of these alpha cuts of the possibility distribution. You're able to bound the probability with 1 minus the alpha. So we're able to construct or sort of convert the probability distributions to these possibility distributions. And what's shown here is an example of some parametric distributions on the top. On the bottom is their possibilistic representation. And we're also able to do the same with probability boxes. So on the top here is essentially a p-box version of the previous distribution. On the bottom is shown the possibilistic representation. Okay, so how do we push these through sort of general functions? The key message here is that you sample the input space, you evaluate its membership in the input, and then you retain that in the output space. So on the top left is shown how you would do this for an interval using just a simple grid search. So I just sampled the space around the interval, evaluated the membership, pushed those through the function, and then on the output space, I've just retained the value of the possibility. And that kind of gives you like an approximation of what the interval looks like. And then in the fuzzy case, it's essentially the same, except the membership function is graded. And on the right is shown a similar strategy, but just using random sampling. So here I've just randomly searched through the input space, and you get this kind of dusty cloud of membership values, and that can give you an approximation of your output possibility distribution. Okay, so that's in sort of the one-dimensional example. When moving to multivariate operations, we need to account for dependence, and there are three ways that there are three functions that we know how to account for. So essentially, you can take two marginal possibility distributions, pass them through one of these functions, and then the output structure basically gives you the joint representation. And we know then there are three functions you can use. There's Zade, independence, and Fréchet. Zade gives you sort of a perfect correlation, a stochastic sort of correlation equals 1. Independence is independence, and Fréchet is the interesting one in this presentation, which is for unknown dependence. So I'm just going to show you what it looks like when you use this for the sum. You get these three different possibility distributions, and the Fréchet example, the unknown example, contains the other two examples. And it's really unfortunate that my LaTeX didn't render here, but what I'm going to show you here is just an example of doing this through a reliability function. So there's some performance function that was going to be shown, but I guess since it's a black box example, you don't need to know what it is. But the two input random variables are two standard normal distributions with an unknown correlation. And then the reliability of the problem is given when this performance function is less than 0. So when you run this sampling-based strategy, here's the possibility distribution that you get out. And then you basically can find all the values which are less than 0. And from there, you can bound or get interval bounds on the probability of failure. And here, I've just done the same, but with second order Monte Carlo. So I've scanned through a whole bunch of correlation coefficients. And what's shown is also their respective probabilities of failure. And you can show basically that all of these probabilities are contained in the interval. Another way of visualizing this is that you can compute the p-box bounds from the possibility distribution, and then when you can show that all of the second order Monte Carlo samples fall within its bounds. Well, thank you very much.
Can I ask a question? You showed a way to go from distributions to possibility bound to possibility bounds, and from p-boxes to possibility bounds. What is the added value of this? What do you gain when you transfer from one certain number to the other? I mean, I can probably see the distributions to possibility, but how about p-boxes to possibility?
Well, if you don't have dependence assumptions, if you don't know the dependence between the random variables, then what do you do in that instance? So the idea is that you can convert them to a possibility distribution and then run them through this kind of method and get bounds and output quantities. And
so to be able to drive them through black box models.
That's right, yes.
Okay, and how many samples do you need? How many samples do you use for that sample?
It's depends on your dimensions. So in that example, it was 2 dimensions. So I used around 10,000. It was enough to get good convergent bounds. But when you're running something like second order Monte Carlo, it would be orders of magnitude there.
More expensive.
Yes.
Okay. Any other questions?
To get those possible stack outputs, what do they make statements that, I mean, engineers are caring about? What can you conclude from it?
Well, you could get bounds on sort of probabilistic quantities that you may be interested in. So things like failure probabilities, quantiles, moments, all these things would be derivable from these.
In my reality, and I presume most of us, we do a lot of simulations with black box models, which are expensive. And for those doing, let's say, CFD, it's super expensive. And doing analysis such as nonlinears or CFD with Monte Carlo is a nightmare. And based on my understanding, you have a method that reduces in orders of magnitude comparing to Monte Carlo. Did I properly understand it? Where's the catch? Where's the catching? What's the limitation?
It's a good question. It's probably it's not cheaper than a single Monte Carlo simulation. So if you have a known distribution function, you could it would probably be around the same cost. But if you didn't know the correlation between your input distributions, you'd have to you'd have to repeat Monte Carlo simulations with different scans of correlation coefficients, and it's cheaper than that. Applying something like this in a CFD model or a finite element model, you'd probably have to use a surrogate because it would take millions of samples to really get a resolution of those kinds of structures that I was showing.